Okay, we're going to do our second example problem. It's 3.5. It involves a long jumper jumping on flat ground. Okay, this is a little bit different than the other problem because this one you actually have an angle at which the initial velocity is at. So you are going to have both x and y components. The other problem, all we had was the initial x component. The y component was 0 because it was launched horizontally. Okay, so in this problem, you're also going to have some symmetry during the jump, meaning whatever happens in the first part also happens in the second part. The initial velocity is equal to 11.0 meters per second at an angle of 20.0 degrees. If we set that up, this would be our initial velocity. This would be our initial velocity in the x direction, and up would be our initial velocity in the y direction. And that would be a right angle. Hopefully that green's good enough to see. Our angle here would be 20.0 degrees. We use sine and cosine to find the x and y components. If you were to do that, VIX should be equal to VI cosine of theta. So VIX would be equal to 11.0 meters per second cosine of 20 degrees Celsius. 20 degrees. If you multiply that out, you get a positive 10.3 meters per second. All right, VIY then, since it's opposite the angle, it's going to be equal to VI sine of theta. So VIY is going to be equal to 11.0 meters per second sine of 20 degrees. We calculate that out, so it's 3.76 meters per second. Now that's also going to be positive. The reason it's positive is because we have a positive 20-degree angle. That means you're launching up, and you're also launching to the right. Okay, I'm going to erase that now, make a little room here. As I'm erasing this, you notice that there's 3 sig digs on both VIX and VIY. Okay, the next step, you would think that you could actually solve for how far the person jumps now, but you can't. Typically after solving for the components, you have to find the time of flight. Okay? You could do that 2 ways. You could find half the time of flight and then multiply by 2, or you could just find the whole thing. I like to solve for the whole time of flight. So I will use our typical first equation, which is VFY equals VIY plus GT. Now we know what VIY is. It's positive 3.76. VFY, though, we also know, because if it goes up with 3.76, it also comes down. So our little picture will look like a ball being thrown up and then coming straight back down. The velocities would actually be the same, but opposite direction. So let's solve for time. VF, I subtract VI first, and I divide by G. I'm going to substitute my numbers in. Remember, negative 3.76 meters per second. That's where students make the usual mistake. Minus 3.76 meters per second. Sometimes students will think that the top is 0, but negative 3 minus 3.76 is going to give you a negative number on the top. Divided by negative 9.8 meters per second squared. The one thing to notice about time is that it can never be negative. So I have a negative number on the top, I'm dividing by a negative number on the bottom. This is 0.767 seconds. This is a number that you're going to need to know in use. Alright, so those are actually the most difficult parts of this problem. At least I believe so. So part A says, how far did the object go in the x direction? That's displacement in the x. We also like to call that the range. So part A, you only have one equation. X is equal to VIX times the time. Remember that the acceleration in the x direction is 0. That's why we don't have any acceleration in the problem here. The velocity is constant. So x will be equal to positive 10.3 meters per second times the entire time, 0.767 seconds. When you multiply that out, you will still have 3 significant digits. And your answer will be, oh, I think I just wrote down the answer for the last problem. Your answer will be 7.90 meters, positive, because it's going to the right. All right, one last step, part B. Part B is asking, what is the maximum height the person reached? Now, if you think about it, it's the same thing as throwing a ball up and stopping at the very top of its throw, or of its peak, okay? At the very top, we know that the velocity in the y direction would be equal to 0. So for part B, I have a ball, I throw it up, it stops at the top, the velocity is 0. My initial velocity is still a positive 3.76 meters per second. So in this case, I'm going to use the second equation, VFY squared equals VIY squared plus 2GY. Make sure I put my vector signs in there. Okay, the final velocity at the top would be 0. I'm going to solve for y. Y is equal to negative VIY, because I have to subtract that to the other side, divided by 2G. I plug my values in. Make sure I don't forget that squared. It'd be negative 3.76 meters per second squared divided by 2 times negative 9.80 meters per second. Try to cram that in there. Alright, so my final answer, y, will be equal to 0.721 meters. That is also positive. It's positive because the ball stops above where it was thrown. So let's do a quick recap of this problem. Step 1. Find components. Find the components. Step 2. Find the time. Now remember, that could either be half the time of flight or the whole time of flight. If it's half, Make sure you use the proper one when you find the x value. And the last step, and I kind of laugh at this one, is to do everything else. Okay, that's the second type of example problem where you're actually going from flat ground to flat ground and you have initial components for the velocity.